Okay, last assignment, assignment 13. Almost ready for the final exam. This assignment, the past few assignments, and also important on the final, will be these four circuits. RC circuit, RL or LR circuit, LC circuit, and RLC circuit. So take a moment and see if you can summarize the behavior of these three circuits. Just a brief review before we dig into problem 2, the first problem really, in assignment 13. So just see if you can answer this. This is kind of a preparation for this assignment and for the exam. So the RC and the RL circuit, or LR circuit, follow two behaviors. One is a charging behavior, where a quantity starts at 0 and it exponentially, in the limit of t equals infinity, approaches some limiting value V max. And so this equation describes this behavior. When t equals 0, this is a -1, and V starts at 0. And when t becomes very long, this becomes 0, and V becomes V max. And the other behavior is the decaying behavior, described by the second equation, where at t equals 0, e to the -0 is 1, and V starts at V max, and it decays exponentially in the limit as t goes to infinity to 0. When t becomes long, e becomes 0, and V becomes 0. And since how long this takes to occur is an infinite amount of time, we characterize the time it takes by the time constant tau, which tells us mathematically how much voltage is there after a time equal to the time constant. And we know that it decays about 63%, or about 37% remaining of that value, and each next time constant the same behavior happens, whether it's charging or discharging. And the time constant for the RC circuit, of course, is R times C, and the time constant for the LR circuit is L divided by R. So in the first part of question 2, when the switch starts completely open with no charge on the capacitor and we close it here, what happens is the battery sends current through this resistor onto the capacitor, charging it, and charges leave this side going back into the battery. And so we have a circuit where the capacitor is charging and there's current through the resistor, and the capacitor is charging. Of course, there's no current inside here. And it follows this charging behavior. For the capacitor, the voltage rises and the charge on the capacitor rises to some limiting value, while the current starts at a very high value, and as the capacitor charges, the current and voltage across the resistor is going to decay exponentially according to the same time constant, which is this times this. And at the end of that behavior, this will be charged, and then when we close the switch here, the capacitor will now discharge through the inductor with no resistance in the circuit. This is an idealized circuit, and it has no resistance. In real life, there would be a little bit, but we could have one where the resistance is very small, And this is called an LC circuit, and this follows an oscillating behavior. The capacitor discharges current into the inductor until the charge on the capacitor goes to 0. But now there's a current in the circuit, and energy from the capacitor is now in the inductor, and that energy will keep driving the current. Even when the voltage is 0, it will drive the current and recharge the capacitor with the opposite polarity, transferring all of its energy onto the capacitor. So the behavior of the LC circuit is an oscillatory behavior following either a sine or cosine function. And here we have a cosine, so it would start high and it would oscillate, and an oscillating behavior is a repeating behavior. So the way we describe that is by the period of oscillation, how long it takes to complete one cycle. That's called the period, and you see that in the equation. And so when the time on the clock time, the time on the x-axis, reaches this time, let's say 10 milliseconds, then you'll have the cosine of 2 pi, which is a complete cycle of 360 degrees, or one complete cycle. So that's how this behavior works. And this determines how high or how low the voltage goes, because the cosine will oscillate between 1, 0, negative 1, 0, 1, 1, 0, negative 1, 0, 1. And so this is a repeating behavior. And in the absence of any resistance, it oscillates back and forth like a never-ending pendulum, or a never-ending oscillation of a mass on a spring. Of course, in a real system, there will be some resistance, and that's the RLC circuit, which I won't talk about in detail now, but it's an oscillating circuit where the energy slowly goes away. So it oscillates and it decays. So it has this behavior and this behavior combined. And if you look at your equation sheet, you'll see the exponential function in front of the oscillation function. So the oscillation slowly decays, or fast, depending on the variables, the quantities, to 0. So in problem 2, when we start the charging behavior, you do have to know that the capacitor starts at 0 and it will charge. So the capacitor is going to follow this behavior. Whereas the current, since when the capacitor is empty, the current will start high, and when the capacitor charges, it goes to 0. So the voltage across the resistor and the current through the resistor will follow this behavior. And what I didn't mention is this is V equals V max. It could be Q equals Q max. It could be I equals I max. And the same way here, we just put it in one form, but if it's the voltage, it would be the voltage across the resistor equals the maximum voltage, 12 volts, will decay to 0. And in this circuit, you see that the inductor is dangling, and so nothing happens in the inductor because no current is going to go through the inductor because it's not closed. It doesn't form a closed loop in the circuit. So the first problem 2 is entirely an RC circuit problem. And if you're calculating a quantity from either of these equations, supposing we want to know the current through the resistor over time, since that starts high and goes to 0, we would write the equation this way. The current through the inductor will be I max, which is using Ohm's law. We get I equals V over R, so 12 volts over 20 ohms, that's the maximum the current will be, and it's going to decay according to minus T times the time constant, which is RC, and R times C gives us 800 milliseconds, right, because this is millifarads, or 0.8 seconds. And so by putting whatever time you want in here, you can calculate what I is at any particular time. And you would do the same thing for all the other quantities, only you have to be careful whether it's a discharging or charging behavior. So moving on to the next question, which follows from this, number 3, the switch is in this position. The capacitor is fully charged, 12 volts across the capacitor, no current because the capacitor is charged, no voltage, so 12 volts here, 0 volts here, no current, then the switch goes down. So what do we know? Two things. One is the charge on the capacitor can't change instantaneously, so this starts at 12 volts and fully charged. But since there's now a closed loop for it to discharge through, it will start to put current through the inductor, and that change in current will cause the inductor to induce a voltage which is equal and opposite to the 12 volts here, for two reasons. One is that's what an inductor does. It induces a voltage, but why 12 volts? Because by Kirchhoff's law, it has to match this voltage. So it can't stop the current. It just slows it down. And as this discharges, the voltage and the charge across here will go down, and this will go down with it. Why? Because the current isn't changing as fast, right? The voltage across the inductor depends on the rate of change of current. And finally, when the capacitor is fully discharged and there's current in the circuit, it won't be changing. And so for an instant, the voltage across both of these elements will be 0, but the current will be at a maximum value. So that's going to defy your intuition, because how can you have current without a voltage? It's just like, how can an object move? An object moves. Once it's moving, it will move. Once there's current, there will be current. It doesn't require any voltage as long as there's no resistance. Just like a frictionless car can move very fast without any energy input if there's no friction. But as the current flows here, it will start to charge here, and the voltage is going to rise, and it's going to slow the current down, and so there'll be a voltage here, and the thing will oscillate in that way. It'll oscillate voltage, it'll oscillate current, it'll oscillate energy, it'll oscillate all those quantities according to either a sine or cosine function. So once again, since when the switch goes down, this is at 12 volts. So we use a cosine function, and this will oscillate between 12 and 12. And the voltage across the inductor is going to be equal and opposite, but looking for magnitudes. So the voltage across the inductor, strictly speaking, would be like this, because it's following it in an opposite sense. But in terms of magnitude, it's going to be the same. And so what's the period of oscillation? It's from peak to peak, or trough to trough, or any two corresponding points on the graph where the cycle is complete. And the equation for that, not deriving it, is that the period is 2 pi times the square root of LC. And it makes sense that the bigger the capacitance, the more energy, the bigger the inductor, the more energy, and both of these things being bigger will make the period longer. So that makes sense. And so we can get any value for these equations by getting the period. But when this discharges to 0 and the current reaches the maximum, don't make the mistake that the maximum current in the inductor is going to be what the current in the resistor was, because the battery is removed. So how do you know how much the maximum current is going to be? because when we get to it, the voltage is going to be 0, and there is no resistance. So the way to do that is to look at the energy equation. So remember, there's no resistance in this circuit, and so it's going to oscillate indefinitely, the idealized circuit. Energy in the beginning is all on the capacitor. There's no current. So the energy in an inductor depends on the current. The energy on the capacitor depends on either the voltage and the charge. Remember, this can be written as 1/2 Q squared over C. That's also equivalent. I'm writing it in this form. And so in the beginning, the energy is 1/2 C times the maximum voltage. So given the C and given the voltage, you can get the energy. And from that, knowing the inductance, you can get what the maximum current is going to be. But the best way is just to do the algebra, solve this for current, and see what you get. Okay, there's a lot of writing here. So here's the equation. Notice I multiply both sides by 2, get rid of the 1/2. And then I solve for I max. And I get I max, taking the square root, is C over L square root times V max. If we had used this equation, that's what you'll see on your equation sheet, instead of this one, in terms of Q max, that's Q max, by the way, we would get that I max is Q max divided by the square root of L times C, which is the same thing that shows up here. So don't be confused by those two forms. It's just different algebra. And that's the way you get the I max. Okay, here's the circuit for the next two problems, 3 and 4 and 5. And the only difference is when we start this circuit, it's an LR or an RL circuit. And the capacitor is out of the original charging circuit. So in this case, we start with an RL circuit instead of an RC circuit. And that's question 4. And then question 5 is once the inductor is charged, and remember, a capacitor is charged by putting positive and negative charge on. An inductor is charged by having current go through it. Because when current's going through an inductor, there's a magnetic field and energy is stored, right, in the conductor. So an inductor can be charged with current. It has energy. And when the switch is closed down in problem 5, you'll have an oscillating RC circuit where the original energy is coming from the inductor. So for number 4, you're doing an RL circuit. Remember, when the switch is first closed, there's no current in the circuit. You can't instantaneously put current through an inductor. And so the inductor will respond by creating a negative 15 volts. And so the circuit starts with no current, no voltage across the resistor, and all the voltage across the inductor. The inductor will charge with current, so the current will go up as the voltage across the resistor charges. And the voltage across the inductor, of course, starts high and will decay. So those are the two behaviors. Those are the equations you need to use. And so the behavior of the LR circuit is different from the behavior of the capacitor circuit. And once that gets to its final state, and the current will be determined by the voltage and the resistance. So 15 volts, the final maximum current going through here will be 3 amps. And so when the switch closes down, the voltage here is 0. By Kirchhoff's law, the voltage has to be 0. And not only Kirchhoff's law, but when that switch closes down, this is uncharged. So the voltage here is 0, and the voltage here is 0, and yet there's 3 amps of current. Again, that's going to confuse you at first, but now current flows in the absence of resistance can flow without any voltage to drive it. But since the current is flowing, the capacitor is going to start to charge, and the voltage across the capacitor will rise as the charge on the capacitor rises, and the voltage on the inductor has to follow that, equal and opposite, of course, because it has to add to 0, and the current, so the current will start high and go down. So the current will be the cosine function, whereas the voltage on the inductor, the voltage on the capacitor, and the charge on the capacitor will be a sine function starting at 0. Let me show you that. So as I said, when the switch goes down after the inductor's charged, the voltage will be 0 here, 0 here, so and the charge on the capacitor. So the charge and the two voltages will start at 0 and will oscillate according to a sine function, whereas the current, so if we plot the current through the circuit, that starts high, and when the current goes to 0, the capacitor will be fully charged. So they're so-called 90 degrees out of phase. And the form of these equations is just what you saw in the earlier part of the video. Cosine and sine functions, where the argument of the cosine and sine is 2 pi over t times t. And the maximum and minimum values will be gotten. Now, so we know this starts at 3 amps, but don't make the mistake to think that this is going to charge to 15 volts because the battery is no longer in the circuit. So how do you get it? Again, remember the energy equation. 1/2 C V max squared, that's the energy when it's on the capacitor, equals 1/2 L I max squared. Or remember, equivalently, this function, this value could be 1/2 Q squared over C equals that. And so by taking the energy on the inductor, that will tell you how much voltage you're going to get, and you'll see it's not 15 volts. Okay, number 6 is just number 4 and 5 combined, all into one question with different values. So once again, when you start, you charge the inductor, and you'll have current in the circuit with no voltage across here, but current, and when the switch goes down, it starts at 0 volts, and the current, the energy stored in the inductor and the current in the circuit will charge the capacitor, and it will oscillate as the current and voltages oscillate as sine and cosine functions, as we saw. Then when you get to 7, we're going to we go back to the RC circuit, but we have a resistor in here. So as it oscillates, the energy is going to slowly be lost, slowly or fast, depending on the resistor, through the resistor. And so the equations for that are on your equation sheet. If you have trouble with those last 3 problems, 7, 8, and 9, which are on the LRC circuit or the RLC circuit, get in touch with me. I'm going to try and post this now. It's already long enough. Oh yes, and by the way, I make the videos if there's information that you think you need that I'm not posting in the videos. By all means, send me an email and ask me to post information. For example, say, no, we need help with 7, 8, and 9. Please make a video on those, or I can extend this video to include more of that. So don't be shy about asking for help.